Oh, hello everyone. Hello everyone. Perfect. Okay. Oh, some familiar faces. Welcome, welcome. It's great. Happy to hear, happy to see. Okay, a lot of new faces, of course. A lot of some familiar faces. That's brilliant. Thank you all for joining. Today we have the first webinar, and the topic is going to be circular motion. So I'll go through the basics. I'll give you some tips on how to do circular motion questions, and I will go through some challenging questions. Some of them will be very similar to those that you've done, that you will be doing in the assignment. So the first question: have you done circular motion at school? 1 for yes, 0 for no. Please answer in the chat. Okay, good. So a nice mixture, some zeros, some ones. Okay. And the second question is, how many questions from circular motion have you managed to do already? 2, 0, all but 4. Ooh, the first section, 4, 6. Okay. Some zeros, that's fine. Okay, so I'd say, all right, so not too many, and that's absolutely fine. So yes, my name is Vlad, and I am the academic coordinator for COMPOS. I am also the author and co-author of many of the assignments that you will be doing. Let's see, yeah, probably co-author of most of them, and yes, so originally I'm from Russia, and when I went to university, we had a similar school for students that could study physics from their homes, even before the age of the internet. At that time, it was by post. So you would receive the assignment in the mail. You would do the assignment. You would send it to the university, and they would mark it and return it to the students. I haven't done that course when I was at school, but I saw students that come in from the university, and I a little bit envied them because they were more prepared than I was for university. And this is what we try to aim. We want you to be prepared for university and for your physics futures, of course. I like to say that if you want to be good at sports, you need to train every day. If you want to be a good musician, you train every day. If you want to be a good physicist, you train every day. And at COMPOS, we provide you with that training. It doesn't matter how talented a person is, they will never become a world-class athlete if they don't train a ridiculous amount of hours, a ridiculous number of hours. So that's what we ask you to do: at least 4 hours of work on top of the webinar and your tutorial session. What will happen next? Once you submit your first assignment, we will mark it. You will receive feedback. And if you do the assignment approximately better than 50% of the students, you will get a place, you will get a tutor who will mark your work every month. So we have 6 assignments throughout the year. and they will mark your assignments, they return them to you, and have weekly sessions discussing them. If you don't get in, don't worry, you still have access to all of our materials. You can do them at your own pace, and you can come to webinars and ask me questions, and I will be more than happy to answer those questions if you have any. Excellent. So I'm happy to answer. I'll answer your questions at the end. Okay, so we'll go through some physics, and at the end, if you have any questions, I will be happy to answer them. And just close that. I'm going to share my screen. Perfect. Okay, so we're talking about circular motion, and the problem one is quite simple. Show that an object is accelerating when it's traveling uniformly in a circle. You learned that acceleration is the rate of change of velocity or speed. Some of you might be confused because between the difference between the two, but acceleration is the rate of change. So it's the change of velocity divided by change in time. And because velocity is a vector, acceleration is also a vector. And that sounds okay until you start thinking about circles. Let's say at point A, your velocity is this way. And let's say you're traveling at 8 meters a second that way. If you, when you're at point B, you're traveling 8 meters per second. 8 meters per second that way. Now, the change in speed, is 0 meters a second because there's no change in speed. But your change in velocity, Can anyone calculate the change in velocity? Roughly. What's the change in velocity between A and B? It is not 8. 8 root 2. Ooh, very good. Very good. 85376478221. Well done. I assume that's not your real name. 8 square root of 2. Yes, it is. It is the change in velocity is 8 square root of 2. And I will prove it to you in 2 different ways. The first approach is I call the dumb approach. Is when you you don't use any common sense. You just behave like a robot. So you label this VA, and we label it as a vector. So this is a vector which is going 0 to the right and 8 up. And this we will label as vector VB and label it as -8, 0. The change in velocity is the final velocity, which is VB, minus the initial velocity, VA, which is -8, 0, minus 0 minus plus 8, sorry, which is -8. minus 8. So the change in velocity is a vector like this, minus 8, minus 8. This is the delta V, that's the change in velocity. Right. And if you want the magnitude, the change in velocity is the square root of minus 8 squared plus minus 8 squared, which is 8 square root of 2 meters per second. So well done. Well done, those. You can say, yeah, it's the change in velocity is minus 8, but the magnitude is 8 square root of 2 meters per second, and the direction is towards the center of the circle, incidentally. So the acceleration is this way. Interesting. Interesting. Let's prove it in a less straightforward way, less like a robot and more like a physicist. You have the final velocity VA, VB, sorry. And we have the initial velocity VA. We need to find VB minus VA. So VB minus VA. So this is the same as VB plus minus VA. So we can do this. We can say VB. This is VB. And this is minus VA. This is VB. And this is minus VA. And we're adding two vectors using the vector addition rules. And we get this is the resultant vector. This is the resultant vector, which is delta V, which is equal to VB minus VA. And if the length of this vector is 8, the length of this vector is 8, this is obviously 8 square root of 2. So two different approaches which give you the same result. And obviously you can see that, all right. And now if there is a change in velocity, as we have seen, there is acceleration. The acceleration is not 0 because there is a change in velocity and there is a change in time. And in the assignment, we will show you, and I think one of the questions is I believe, is to show that, no, I think it's not a question, I think it's an example, that acceleration, the centripetal acceleration is v squared divided by r, with the radius. This is called centripetal acceleration. How well do you understand what I have done in problem 1? On a scale of 0 to 10, please. 10 being I understand completely. 0, I have no idea what you're talking about. Okay, awesome. So when you are moving in a circle, even though the speed is constant, the velocity is changing. And this change is quantifiable. And the acceleration is also quantifiable, which is great. Ooh. I wanted to do these in the opposite order. Okay, so here we will also need to use the law of gravitation. We have studied that in year 12, I believe, and it's a simple law of gravitation, Newton's gravitation law. So if you have two objects, okay. So Caitlin, what I would recommend is going through the assignment on vectors. the COMPOS assignments for vectors, it is from year 12. From year 12, and I have recorded two webinars on vectors, at least 2 webinars on vectors. So you can study vectors by yourself from COMPOS. You can come to my year 12 webinars as well. If you'd like to hear about vectors. I'm going to talk about vectors next Wednesday. Newton's law of gravitation says that if you have 2 objects of mass m1 and m2, separated by a distance of r, the force, there will be an attractive force between them. So Newton's law, universal law of gravitation. The force, the attractive force between any 2 masses in the universe is F equals the gravitational constant multiplied by m1 multiplied by m2 divided by r squared. This is also known as the inverse square law. You have any two objects in the universe that are separated will attract. So let's have a look at the question. A satellite is in a low orbit around a planet of mass m. It takes the satellite time t to make one rotation around the planet, of course. Find the radius of the planet. Let's see. We have a planet and a satellite. When I say it's on a low Earth orbit, what does that mean for us? Low orbit. So it's going in circles. Why is this information significant to us? R is small, but R is not small. I disagree that R is small. Similar to the circumference of the Earth. What is? I think you're right, Daniel. Okay. Yes, Benjamin, your answer, you got the first one too correct. The radius of the orbit is equal to the radius of Earth. That's what we mean when we say low orbit. And there are satellites on low Earth orbit, which are approximately around the Earth in around the Earth in very close to the ground. So, for example, the first person in space is Yuri Gagarin, who flew in space on the 12th of April, 1961. He went around the Earth in 108 minutes. So he was on a low Earth orbit. And it takes a satellite on a low orbit around a planet of mass m. So the mass of the planet is m. We don't know the mass of the satellite, but it's a good practice that if you don't know something, you just say that, oh, it's m. It takes time t to make a complete rotation. Find the radius of the planet. So r is question mark. Okay. So we start by looking at the satellite. And we just draw the satellite separately. So this is our satellite. They usually look like this. And what are the forces? So it's traveling, let's say it's traveling this way at velocity v. And what are the forces acting on the satellite? You can ignore air resistance, of course. The force of attraction, yes. The force of attraction, so there's a gravitational force. Gravitational force, and we already know that the gravitational force is equal to G m1 m2 over r squared. So F, the gravitational force, is gravitational constant, mass of the satellite, mass of the planet, divided by r squared. Now here, r is the orbit of the the radius of the orbit, but it's also the radius of the planet. So we're safe to assume. And that's the only force. That's the only force acting. So when you say centripetal force, you need to understand the centripetal force is the gravitational force. Centripetal force is not a new force. Centripetal force is the force of gravity in this case. If you take a mass on a rope, and you spin the rope, the centripetal force is the tension in the rope. If you have a car driving around a bend, the centripetal force is the friction from the road, between the road and the tires. So this is the gravitational force, also centripetal force. All right, so we write down Newton's second law. Newton's second law. Newton's second law says that mass times acceleration is equal to the sum of forces acting on the satellite. So the satellite of mass m, mass and acceleration, and it's equal to the total, well, acceleration we already know that it's moving in circles, so it's mv squared over r. We already know that, mv squared over r. And it's equal to the total force, total external force acting on the satellite. And there's only one force acting on the satellite, which is the gravity. So it's G m capital divided by r squared. And look at that. We have m cancels. We have r cancels. So we need to find, so we have from here, we have v squared is equal to gm over r. Right. So Paris, what exactly differentiates the tension on the object and the gravitational force in terms of the centripetal force and its effects? Look, the centripetal force is whatever is causing you to travel in circles. Traveling in circles is not natural. If you are in deep space and you take an object and you throw it, it doesn't go in circles. It just goes straight, goes in a straight line. But if there, and I will demonstrate. So let Okay. So let's say you have an object. It goes, and you put a trace. So this is a positively charged particle. This is another positively charged particle. And when you start, it just goes in a straight line. So particles tend to go in a straight lines. However, if you place a negative charge, it will, well, attempt to go in a circle, if you're lucky. Okay. Too fast. Okay, this is more or less going in circles. It is slingshotting. So if it's going in circles around because there's a force, if there was no force, it would be traveling in a circle. So when we say centripetal force, it's a force that's causing you to turn. And for example, if you, as I already mentioned, if you have a car on a road, the car needs to turn. The car has 4 tires, which help the car to turn. Because if there were no tires or it was an icy road, the car would travel straight. If there was no grip, the car would go this way. But because there are tires and because there's grip of the tires against the road, the car is traveling in a circle. So there is a force towards the center, we call the centripetal force, and in this case, it is the friction. If you have a mass on a rope, and it's going in circles, circles, not blobs. You have a mass on a rope and it's going in circles, then the tension is the force that causes the mass to turn into the circle. Because if there was no tension, it would just go in a straight line. Tension is a force in a rope. Gravitational force is the gravitational attraction between objects in space. So these are completely different forces. They even have this different nature. Right, so coming back to our satellite. Sorry, I've been talking all day. My mouth hurts a little. Well, my jaw is tired. Okay, so we have, coming back to this, we don't know the speed, but we do know the time period. So how do we link the time period and the speed? Okay, so the time period and the speed. So the time period is distance traveled. Time is distance divided by speed. Therefore, the time period is the distance, which is 2 pi r. 2 pi r is the distance traveled, and the speed is v. So here we can make v the subject is 2 pi r divided by t. And we can plug that into here, and we get 2 pi r over t squared equals gm over r. We get 4 pi squared r squared over t squared equals gm over r. And we have r cubed is equal to gm t squared divided by 4 pi squared. And here we need to pause for a second to appreciate that this is known as Kepler's second law. Second? Yes, second law. That the radius of the orbit, the cube of the radius of the orbit, is proportional to the time period squared. And that's one of the things that led Newton to discover the law of gravitation. Kepler's second law. Kepler's second law. Oh no, sorry, third. It must be third law. I've just made a fool of myself. Yes, Kepler's third law. The square of the orbital periods of the planet is directly proportional to the cubes of the, well, in this case, radius of the orbit. Kepler's third law. Kepler's third law. Third law. So Kepler was an astronomer, very famous one, and he discovered the laws of how planets move around the sun. Very, very important laws, which we still use. So yeah, and of course, if you want the radius is equal to the square root of cube root gmt squared over 4 pi squared. That's the answer. So you can express the radius like this. Right, hope that makes sense. So, and with this, we come to this. The time period of the G is the gravitational constant. G is the gravitational constant, and it's equal to 6.67 times 10 to the minus 11. And the units are bizarre. So if you have force, G m1, m2 divided by r squared. So I'd say it's going to be newtons, meters squared, kilograms minus 2. Yeah, bizarre units. Approximately equal to, of course. It's not exact. Sorry. Kevin, do you have a question? Sorry. Your hand is raised. Okay, that's fine. Good. So moving on to the ISS. ISS is the International Space Station. You might have heard about it. And sometimes early evening, when the sun has just set and the sky is dark, you can see it, and it's beautiful. So what you need to be looking for, you need to be looking for a very bright star, perhaps just as bright as Venus, and you will need to it moves across the sky quite quickly. You see that it is moving. It's not flashing. If it's flashing, it's an aircraft. It will be constant brightness, and it just goes across the sky quite quickly. It takes about a minute and a half to traverse the whole sky. This is the International Space Station. And you can track the International Space Station on a website called ISS Tracker, and you can see where it is, and you can see it, and then you confirm, oh yes, it is the International Space Station, and it's fascinating. Well, at least to me. It is well, G was derived experimentally at first with heavy masses, and then I don't know the current value of G. I don't know exactly how it's calculated. Initially, it was calculated experimentally. Perhaps nowadays there's a different way of calculating it using constants. So I'm not 100% sure. At the moment, I haven't looked it up. Just use it in calculations. The time period of ISS, so it takes 91 minutes to go around the planet once. Calculate the centripetal acceleration. Well, you do need to know that the height of the ISS above the ground is only 400 kilometers. So the height above the Earth for the International Space Station is just 400 kilometers. And that's not a lot if you think about it, because the radius of the planet is 6,400 kilometers. That makes the radius of the Earth is this, so the radius of the ISS is approximately 6,800 kilometers. So not at all big. Calculate the centripetal acceleration. All right, so we know that the time period is 91 minutes. And we also know that the time period is the distance, so it's 2 pi r divided by the velocity v. We know that the centripetal acceleration is v squared divided by r. So from here we can express v equal 2 pi r divided by t. And we can plug it into here. We get 4 pi squared r squared divided by t squared r. Okay. And yeah, so we have this cancels. We have 4 pi squared r divided by t squared. Good. So this is the acceleration of the ISS, and we can calculate that. So that is approximately 4 times pi squared, so 3.14 squared times r, which is 6,800 meters, 6,800,000 meters, divided by t, which is 91 times 60. Is there a formula data sheet? Well, the formulas are embedded in the in the assignment, so they're in the text. So any exam board is different. So if you're talking about school exams, then probably yes. With us, you can just use any formula sheet you like. Just use anything downloaded from the internet. Whatever resource you can get your hands on, you can use it. So yes, acceleration. Just need to find, and it's 4 times 3.14 squared times 6,800,000 divided by brackets 91 times 60, close bracket, squared 8.96. 8.96. And this is acceleration, so it's meters per second squared. What significance do you think that is? What is the significance of this value? It's almost the same as the value of g. So why do you think it's not the same as the value of g? Because we're not on the surface of Earth, of course. This is the value of g at that height, 400 kilometers above the ground. Well done. That's really well done. So the second question is calculate the gravitational field strength at that height. So let us do that. So we know that the ISS, so we have the ISS here, and we have the ISS. It's much bigger. It's the size of a football field. Imagine it's a satellite, the size of a football field. It's absolutely massive. And there's a force. And we know that the force is equal to G, mass of the International Space Station, mass of the planet, divided by the radius squared. Now, the force is also known as the gravitational force, so it's mg. So this is equal to mg. That means that m cancels. M cancels, and we have g, the gravitational field strength, is equal to g m over r squared. So this is the question for question B. And we can work this out. So it's 6.67 times 10 minus to the power minus 11 times the mass of the planet is 5.97 times 10 to the 24 divided by radius, so 6,800,000 squared. And so 6.67 minus 11 times 5.97 times 10 to the 24 divided by 6,800,000 squared is 8.61. Okay, so a little bit off. 8.61. But this is because I got the approximate value for meters per second squared. This is what because I got the approximate value for the orbital time and the approximate value for the radius. So if we adjust, if it may take 92 minutes, perhaps. Yeah, if we take 92 minutes, I guess. Okay. Yes. Okay. Yes. Thank you. So these values are very close. So they're not the same just because the values for the height and the values for the minutes are approximate. And but you can see that they're not coincidences. F equals to mg because it's the gravitational force, mg. Because F is the force of gravity, but it's also known as mass times g, mg. All right. Oh, I see some people from my old school. Hello. Okay. Right. So a bus is making a sharp left turn, and describe the forces exerted, experienced by a passenger. Explain the difference between the centripetal and centrifugal forces. Now, at school, and I can't stress this enough, please never use the word centrifugal. You will make your teacher mad. And if you use the word centrifugal in an exam, you would probably get 0 marks for that question, just because the examiner would be not happy with you. The reason why physics teachers and examiners do not like this word is a good reason, because people talk about centrifugal force without understanding what it is. It is not a real force. It's an imaginary force which only exists in non-inertial frames of reference. I will talk about non-inertial frames of reference in a bit, but basically, it is very common for people to say, especially race car drivers, for example. They say, "Oh, you're driving your car, you're going into the corner, and the centrifugal force throws you out." Let's talk about this. So a bus is making a sharp left turn. So there's a bus. There's a bus. And this is the front of the bus. These are the headlights. And you are sitting here. This is you. And the bus is making a sharp left turn. You experience a force. What is the direction of that force? You experience a force. What is the direction of that force? Anyone? Left, of course. You experience a force to the left. Where is that force coming from? So can somebody tell me, where is this force coming from? It is coming from the friction between you and the seat. Or, if you're unlucky enough, it's coming from the window, which is hitting you on the head. Okay, if you're not holding strong enough, but there is a force. There's a force to the left, and which is the centripetal force, which is the friction, or normal reaction. Why do people think that there's a force to the right? Why do people think that there's a force pushing you to the right? Because they sit in the bus makes a sharp left turn, and you say, "Oh, there's a force to the right." What's going on? Why is it? Why is it? Why is it like that? No, it's nothing to do with Newton's third law. The non-inertialness. Yes, very good. It's the non-inertialness. Force to the right. There's no force to the right. Look, the thing is that if there was nothing pushing you to the left, if you're well done, Matthew. Matthew, that's a brilliant answer. If you were to continue traveling, if there was nothing to push you to the left, you would carry on in a straight line, whereas the bus would turn. So it's actually the bus is moving left, and it's hitting you from the right. It's the bus going into you, not you going into the bus. And that's very important to understand. The bus is making a left turn and you want to carry on going forward because your body wants to keep going forward, but the bus hits you from the right and it makes you go left with it. And the force that you experience is called the centripetal force. The centripetal force is the force that causes you to turn. And I think that's marvelous because it's so non-intuitive, because you think of, well, yes, if you turn left, there's a force to the right. There's nothing pushing you to the right. There's only forces to the left which cause you to turn left, because if there was no such force, you would keep going straight on and you would be thrown out of the bus. And that's what happens if you didn't have a window and you were, instead of a seat, there was a smooth slide. You would slide out of the bus. Okay, so that's it. That's the thing. The bus makes a sharp left turn. The force to the right of the bus is an imaginary force. So this is the centripetal force. Centripetal force. Force makes you go left. So what is the centrifugal force? The centrifugal force, and I can't stress this hard enough, never to be used in a school setting. So please be careful. If you want to know why, ask your teacher. Centrifugal force. Now, to understand centrifugal force, now you have to say this. Now, I'm sitting in the bus. This is me sitting in the bus. For all I know, the bus is completely stationary. The bus is not moving. To me, the bus is not moving. Not moving. Moving. Imagine you cannot see out of the window. There's no way you can see what's going outside. If the bus starts to make a sharp left turn, you experience this as if you're being thrown to the right. That's some magic force. Perhaps what's that? What was that force? Expelliarmus or reducto is suddenly something invisible kicks you to the right and you hit the right side of the bus. A force out of nowhere. So you're sitting in a stationary bus and suddenly you're thrown out. You're out of your seat. Force out of nowhere pushes you. pushes you. So if you assume that the bus is stationary, then that is what you experience. This is called centrifugal force. Centrifugal force. Force. And centrifugal force is equal to, well, minus mv squared over r. So it's technically the same thing as the centripetal force, but it's in the opposite direction. Now, centripetal force is a real force because it's the seat pushing you. That's real. Centrifugal force is not real. It's an imaginary inertial force. Do you understand? Do you understand the difference? Do you understand the difference? And centrifugal force kind of makes sense because I am in a bus. The bus is not moving. I don't see the bus moving. The bus is, I am the bus. But suddenly something very weird happens and I'm being thrown. Okay. So what is it? Centrifugal force it's an imaginary force which only exists in non-inertial frame of reference. An imaginary force that only exists in a non-inertial frame of reference. A non-inertial frame of reference, and so inertial frame of reference is a frame that is moving with constant velocity. Non-inertial frame of reference is an accelerating frame of reference. And the bus is a non-inertial frame of reference because it is accelerating. So once it is accelerating, right, constant velocity relative to that's a good one. Constant velocity relative to a well, you can't say stationary because what is stationary? Well, technically, it's an inertial frame of reference, frame that is moving with constant velocity relative to another inertial frame. Yeah. So yes, relative to other inertial frames of reference, but that's kind of a cyclic definition. It just popped out of my head how to define how to resolve that conundrum. Oh yes, an inertial frame of reference. Yes, an inertial frame of reference is a frame of reference where if there's no force on an object, it won't accelerate. Okay, basically, inertial frame of reference is where the Newton's first law works. So how does that work? Oh, that's very simple. If I take a toy car, and put it on my table, it will not move because I am in my room, and my room is an inertial frame of reference. Imagine I take the same toy car and I put it on the floor of a bus. I'm not pushing the car, and yet when the bus slows down, the car will move. Yes? Do you all understand that? If I place the car on the floor of a moving bus, when the bus slows down, the car will move forward. So I'm not pushing the car, and yet the car is moving forward. So the bus is not an inertial frame of reference because it's accelerating. But my room is an inertial frame of reference. And that's the difference. So in inertial frame of references, Newton's laws work. In non-inertial frames of reference, the laws of physics are thrown out of the window. At least Newton's laws are. So are we taking air resistance into account in this scenario? No, why would you? You're in a no. You ignore air resistance completely. If you put a ball in the floor of, or if you put a tennis ball on the floor of the bus, inside the bus, when the bus slows down, the ball will move forward, and when the bus accelerates, the ball would move backwards, relative to the bus, of course. The video will be posted on YouTube roughly an hour after I finish. True, Martha, that is very good. The planet is moving in a circle, so it is accelerating. How is my room an inertial frame of reference? That is true. However, this acceleration is incredibly small, and therefore it is almost indistinguishable to an inertial frame of reference. So it's approximately inertial. But there is an experiment that you can do. Well, it's called the Foucault's pendulum. So Foucault was a French scientist, and he discovered that if you release a pendulum, it will oscillate, but as the Earth turns on its axis, the plane of the pendulum would change. The direction in which the pendulum swings will change. And this is how you could detect the rotation of the planet using a pendulum. And this is how you can prove that the Earth, in fact, is not an inertial frame of reference. So well done for this question. And let me demonstrate one more example of why you can throw laws of physics out of the window if you are in a non-inertial frame of reference. So imagine you have a pendulum that swings. So in this position, the pendulum is height h above the ground. So the potential energy of the pendulum is mgh, and the kinetic energy of the pendulum, kinetic, is 0 because it's not moving. Just underneath the pendulum, we have a car. And the car is accelerating. So as the pendulum swings to this position, the car accelerates in such a way that it is always underneath the pendulum. So when the car is here, the pendulum is here. When the car is here, the pendulum is here. When the car is here, the pendulum is here. So by the end, the relative to the car, because the car and the pendulum are moving at the same speed, but the potential energy of the pendulum is 0 because it's on the ground now. But the kinetic energy of the pendulum in the frame of reference of the car, so relative to the car, the kinetic energy is 0 because if you look out of the window of the car, the pendulum is moving with the same speed as the car, so the velocity is 0. So conservation of energy doesn't apply here. Look, we have a total energy of mgh, and now we have a total energy of 0. Energy is not conserved in a non-inertial frame of reference. In the frame of reference of the car, energy is not conserved. This is because the car is a non-inertial frame of reference. Okay. By the way, I haven't mentioned, but I have recorded last year. I have recorded a webinar on circular motion. It has a different problem set, but it does contain this problem with the car as well. So you can go back and see how I explained it a year ago if you like. See if you like that explanation better. Are there different laws for non-inertial frames of reference situations that not possible to determine? Well, if you know exactly the acceleration of the inertial frame of the non-inertial frame of reference, sometimes you can reverse engineer the laws of physics and see that they do apply. But yeah, just it's a thing to be aware of. In non-inertial frames of reference, things can start moving without you pushing them. Yeah, like the car and the bus. Things energy is not conserved. And lots of weird stuff going on. So yeah, and that is why, because non-inertial frames of reference are so intricate, they require such deep understanding of mechanics to operate fluently, that when you use that in a school setting, the teacher just assumes that you don't know what you're talking about, and they won't get mad. So that is why don't use that. Quantum mechanics. Well, no, quantum mechanics is another area where laws of physics break down. But this is not really to do with non-inertial frames of reference. Okay. So it's a whole other can of worms. So. Okay. Let's have a look. What else? Tangential and normal acceleration. So we have discussed centripetal acceleration, which is also known as the normal acceleration, because it is always at right angles to the velocity. And as a matter of fact, that's one of the reasons that it doesn't do any work. So you cannot change the velocity using centripetal force. Because the work done is always 0. It's another very important. Centripetal force never does any work because it is at right angles to the velocity. There's 90 degrees, and the work is force times distance times cosine of 90, which is 0. Cos 90 is 0, so that's 0. So centripetal force does not do any work, so it cannot not change the speed or kinetic energy. It cannot change the kinetic energy of anything because it is 90 degrees to the direction of motion. What does it mean? What does it mean when you refer to the frame of reference? So a frame of reference is a set of clocks and rulers that you use to measure space and time. So for example, in the frame of reference of the room, I'm in the frame of reference of the room. I can say I am standing at a height 0. I am 2 meters from that wall. I am 1 meter from the ceiling, and I am 1 meter from that wall. That is my frame of reference. So I measure everything relative to this room because this is my frame of reference. When I am in a car that is moving, I can measure stuff that I'm sitting 20 centimeters from the left window, 1 meter from the right window. My legs are 15 centimeters from the engine, and the time goes as the time goes in my car. So that's the frame of reference in my car. So for example, there's a bus going along the road at 30 miles an hour. I am driving my car 40 miles an hour. In the frame of reference of the bus, my velocity is 10 miles an hour. So for the people sitting in the bus, they see my car traveling at 10 miles an hour, even though I'm going 40 and the bus is doing 30. In the frame of reference of my car, the bus is moving backwards at 10 miles an hour. In the frame of reference of the road, my car is doing 40 and the bus is doing 30. In the frame of reference of me, the trees are going backwards at 40 miles an hour. The houses are moving backwards at 40 miles an hour. And if there's a plane above my head that is doing 200 miles an hour, that in my frame of reference, it's doing only 160. And in the frame of reference of that plane, I'm doing 160 backwards. So this should give you a feeling of what a frame of reference is. Okay. Right, so I have mentioned that the centripetal force cannot do any work because this is because there's no parallel component. No, centripetal force never has a parallel component. If it has a parallel component, it's not a centripetal force. It is a tangential force. So I hope that makes sense. Right. So find the acceleration of a mass on a rope when it is at B. So to answer this question, we have to draw the forces acting on B. And the forces are there is the gravitational force mg, and there's the tension force T. Why do frame of reference fall apart when you consider light? Oh. Well, they don't. They don't fall apart. It's just light behaves differently. I'm not ready to go into this. Light. Good question there. Okay, so there's an angle theta, so there's also an angle theta here. So you can say you can choose two directions. So usually you take a direction vertical and horizontal. Here we take a direction along the rope and perpendicular to the rope. Okay, so we can call it the y-axis, and this can call this the x-axis, right? So in the y-axis, we have mass times acceleration. Weight is always vertically down. I mean, it's a gravitational force. How do you know that the weight is acting that way? Because we get confused in the question. Yeah, so it's gravity. We have a mass on a rope that is going in circles. It's a vertical circle. Oh, that's a fair point. That's a fair point. Usually the question does state that something like the magnetic acceleration motion on a rope when it is at point B, the mass is the plane the mass is traveling in the vertical plane. So when we say vertical plane, so means like this, and that means it goes like this. If it's a horizontal plane, then it's like this. It's moving in a circle in the horizontal plane. So yeah, if you're unsure, just send me. If you're not sure in a particular question, just ask me in the webinar. I'm happy to explain a question, and I will change that question for the future so people don't get confused. So sorry if it's confusing, but usually there is an indication where it's vertical or not. Okay, so in the y direction, mass times acceleration in the y direction is provided by two forces, the tension force plus the component of mg. You can see mg has two components, and I'll label them with red. So there's a component of mg along the y-axis and a component of mg along the x-axis. So this is mg sine theta, and this is mg cos theta. Mg cos theta. The tension generally dependent on material, though? No, generally it is not. Generally, it is only dependent on the external forces. Yeah, G points downwards. The webinar will finish in 9 minutes. I'll try to finish on time. So the tension force plus the component of y, so mg cos theta. And okay, so that's the acceleration along the y-axis. We call it the normal acceleration. We call it the normal acceleration. So from here we can work out. Well, we need to find the tension first. Now in the x direction, So mass acceleration x is equal to minus mg sine theta, because you can see that this force causes it to slow down. Mg slows it down, so the acceleration is negative, and that makes sense. And instead of x, we call it acceleration along the rope. So it's tangential acceleration, a tau, ma tau. We also know that the normal acceleration is v squared over r. And yes, so from here, from all of these three, we have mv squared over r equals t plus mg cos theta. And here we have m a tau, well, ma tau is equal to minus mg sine theta. Well, we need tension. We need tension to find the acceleration. So ma, the normal acceleration, we need velocity. So we have unknowns. We have v is unknown, t is unknown, and a tau is unknown. So we have two equations, but three unknowns. Two equations, three unknowns. That means that we probably can't solve these. So even before we attempt to solve these simultaneous equations, we need to understand that there are three unknowns and only two equations. G points downwards. Is there a reason why everything in the universe moves in circular elliptical motion? Planets. It is moving in a circular elliptical motion. Well, that's the nature of the attractive forces. Yeah, I mean, it is. Electrons in an atom. Although electrons in an atom we can't say that they move in circles, can we? It's yeah. Well, you have a velocity and you have a perpendicular force. Yeah, they will move in circles. It's because the planets that don't move in circles, they hit the sun and they don't exist anymore. So it's only those planets that survive that move in circles. Others just didn't survive. It's, well, same with an electron. If an electron falls directly onto an atom, it won't become an orbital electron. It will combine with a proton to make a neutron. Okay, and that's what happens in neutron stars. Electrons are pulled into the nucleus of an atom, and they become protons, become neutrons, and the whole star becomes just a giant ball of neutrons. Anyways, we have so we need to resolve that. Oh well, we have conservation of energy. We have conservation of energy that we can use to figure out the velocity, because we know that the velocity here, that we have mv0 squared over 2 is equal to mgh, so it's just raised above the ground, plus 1 mv squared v squared over 2. So we can forget the m, We can double it, so v0 squared is equal to 2gh plus v squared. And h, well, we need to find h, and we can express h in terms of theta. So this section is r. That's easy. This is r. And this is r cos theta. So h is r plus r cos theta. So we put that in here. So we get v0 squared equals 2g r plus r cos theta plus v squared. So v squared is equal to v0 squared minus 2gr 1 plus cos theta. And we can use that in here. Sorry, not here. Here. And now we are down to, well, you can treat it as a third equation. That's the third equation. 3 unknowns, 3 equations, and now it is solvable. Of course, it's not the easiest thing to solve in the world, but it's doable. You can, and from here, you can find the acceleration. So a tau is equal to, you can cancel the m's here. It's minus g sine theta. That's easy. And a normal, the normal acceleration is mv squared over r, which is m over r times v0 squared minus 2gr 1 plus cos theta. Is there anything interesting here? Oh, not really. So it is an is m v0 squared over r minus 2mg 1 plus cos theta. So this is the tangential acceleration, and this is the normal acceleration. And the full acceleration, because it's asking for the acceleration, because the mass on the rope is slowing down, but it's also moving in circles. So we have an acceleration this way, an acceleration this way. So we have the normal acceleration. If you have 3 unknowns and 3 equations, are they guaranteed to be solvable? No, they are not guaranteed to be solvable. It's a general rule, maybe a rule of thumb, but is it not v squared over r? Oh yes, of course, it is v squared over r. There's no m. Sorry. That makes sense. Apologies. If you have acceleration, the normal acceleration and the tangential acceleration, if you want the full acceleration, this is the full acceleration, is equal to the square root of an squared plus a tau squared. So just keep that in mind. Now, I do recommend watching last year's webinar. It's on our YouTube channel. I will post the links on the, what did I say? Isn't v squared over r? Okay. It is v squared over r, but we don't know v, and that's what we did here. We found v. This is the way we found v from the initial velocity, because v0 is the initial velocity. We don't know the final velocity. We did use acceleration is v squared over r. We just replaced v squared with v0 squared minus 2gr 1 plus cos theta. I do recommend going through. I will post the links on Google Classroom, and you can also find the links to our last year's webinars on the website. So if you are still not sure, do have a look. I go through different questions last year, and yes. So Caitlin, have you joined this week? Have you joined more than a week ago or less than a week ago? If you've joined less than a week ago, you will receive the link tomorrow. If you've joined more than a week ago and haven't received the link, then please send me an email. Okay. We send links every Friday because it just takes time. Okay. Yeah. Thank you for joining. I really hope it was useful. If you have any questions, the due date is the 15th, 15th of October. So you have a month. Welcome. In the matrix. Yes. So, but if the determinant of the matrix is 0, then there's no solution. My email address is, or you can find it on the website, compos.web.ac.ox.uk. You can find my email there. Спасибо, пожалуйста. And let's read on the classroom. The notes. Well, on the Google Classroom, no, the Google Classroom pretty much contains the assignment, and it contains the links to webinars. Right. You're welcome. When will the maths assignment webinar be? Next week. Next Thursday, I will do maths. I will do complex numbers. So we do webinars every week, and it goes physics, maths, physics, maths, physics, maths. Welcome. You too. It's up to you, Pratham. If you I will try to make sure you learn something new. But I mean, you can spend your time otherwise. Okay. There are notes to read on the classroom. Well, all the notes that you need are on in the assignment itself. Okay. The classroom is just for you to submit the work. Saheb, yes, happy to answer your question. Is the assignment treated as an entrance for you? Look, if you've done if you've joined, if you did last year, you still need to submit the work. I mean, we won't accept those who haven't done the first assignment, except the entrance criteria is not applied to you because you have a place automatically. That's the general rule. However, I have to mention that we have about 120 places in year 13, and 90 people have applied from last year. So if the numbers increase and we can't accommodate everyone, then we'll have to look at the number of assignments submitted last year, the quality of the assignments submitted this year. So yes, it's not black and white. That I mean, if we are overwhelmed with the number of applications this year from last year's students, we might not be able to take everyone on board. But you will still have the webinars. You can still come in and ask questions. Yes, but as a general, if you've done all the assignments last year, it's safe to say you have a place this year. If you've done the minimum and you've submitted them last minute, there is a possibility that you might not get in this year, but slim. Our reference is supposed to begin after COMPOS is over after the year. Yes, you can request a letter from us if you'd like. We do send letters automatically at the end of the course. We send them automatically, but if you'd like, I should switch off the recording at this point.